Hello everyone and welcome back to Diksha Karnataka YouTube channel, and today in the second PU midterm preparation I am going to discuss not one but two chapters together. So magnetism and matter and electromagnetic induction, both chapters I am going to discuss in today's lecture. So first will be rapid theory revision, and then there will be all questions, all important questions in one video, so you don't need to wait for three different videos. So only in two videos I am going to cover the entire chapter, not only one but two chapters, magnetism and matter and also electromagnetic induction. In the length, in terms of length, they are not super big, but some of the concepts can be very tricky from these two chapters. So without much delay, let me start with the first chapter, that is magnetism and matter. And I request you, if you have not yet subscribed to our channel, definitely subscribe to our channel, and to get all the class notes and everything, you have to join our WhatsApp group. The link is given in the description. You can join the WhatsApp group, and the PDF links will be shared in our WhatsApp channel only. Right? So magnetism and matter, I am going to start with the first. Let's look into the list of important concepts: bar magnet, magnetization, magnetic intensity, and three magnetic properties. These are the major important concepts from this chapter. Also we have Gauss's law of magnetism in this chapter. Now let's start with the bar magnet first. The earth behaves as a magnet with a magnetic field pointing approximately from the geographic north to geographic south. So even though it is not exactly geographic north and south, but approximately you can consider that earth is a huge magnet with its north pole near actual geographic north and its south pole near its geographic south, approximately. When a bar magnet is freely suspended. Now what is the meaning of a bar magnet? So bar magnet means, if you are an ice cream enthusiast, you have eaten chocobar, right? Chocobar ice cream. So it is basically, bar means it's like this, the shape, this shape is called a bar. Okay, so chocobar, even mobile phone, if you are watching my video in a mobile phone, that the mobile phone, this design is also called bar design, mobile phone bar design. Basically it represents the shape. It nothing to do with anything, it is just the shape. Okay, so bar magnet is like this. Any magnet which is like this is called a bar magnet. Right. So when a bar magnet is freely suspended, so if you take this bar and if you suspend it using some thread from the middle, okay, you tie a thread and if you suspend it, then what happens is that it points in north-south direction. One end point towards north pole, one end point towards south pole. Okay. The tip which points towards the geographic north is called north pole of the magnet. So this is called the north pole of the magnet, and the tip which points towards the geographic south is called south pole of the magnet. Okay, opposite poles attract each other and like poles repel each other. So if you bring two north poles, they will repel. If you bring a north pole, another south pole, then they will attract each other. So opposite poles always attract, like poles they always repel. Okay. Now you have to remember that in case of a bar magnet, even if you cut it from the middle, you cannot separate north and south pole. The north and south pole are always there. Even if you cut it, new south pole will appear, new north pole will appear, but you cannot separate a single pole. So that's why it is called magnetic monopole does not exist. Monopole means single only north pole. If you can have a pole having only north pole, then you can say this is a monopole. Unlike in electric charge, okay, positive and negative charges can be separated. You can have a positive charge, you can have a negative charge separately, individually, but in case of magnetism, that is not possible. Okay, so magnetic poles are always appear in pairs. That's why this is the term they are called, or they are always a dipole form. They are always in a dipole form. Okay, a current carrying solenoid also behaves like a bar magnet. So if you take a current carrying solenoid, we have done a magnetic field due to a solenoid, right? So in fact a solenoid, if you take a solenoid, okay, current carrying solenoid, it will have almost, it will behave like a bar magnet. In fact its magnetic field lines etc. can be considered to be equivalent to that of a bar magnet. Now next, the magnetic field lines of a magnet or a solenoid form continuous closed loop. Okay, so magnetic field lines, if you are talking about magnetic field lines, they always form continuous closed loop. So what is the difference between electric field lines and magnetic field lines? Electric field lines do not form closed loop. Magnetic field lines do always be in a closed loop. Why so? So if you consider that field lines will originate from North Pole, okay, and it will end up in the South Pole, but inside the magnet it will go from South Pole to North Pole. Outside the magnet, field lines will grow from north to south, okay. Inside the magnet it will go from south to north, okay. It will happen every time, right? Now let's move on. The tangent to the field line at a given point represents the direction of the net magnetic field B at that point. So if you have a magnetic field line like this, if you draw a tangent, then this tangent will represent the magnetic field at that particular point. So if you want to find the magnetic field at any point, okay, you just have to draw the tangent at that point, and that will give you the magnetic field at that particular point. The larger the number of field lines crossing per unit area, the stronger is the magnitude of the magnetic field. So if the magnetic field is stronger, then field lines will also be more. More number of field lines means stronger magnetic field, less number of field line means less stronger magnetic field. The magnetic field lines do not intersect, common property for all the properties that we have learned. For if they did, the direction of the magnetic field would not be unique at that point of intersection. Same as that we have learned in case of electric field, the magnetic field, if they crossed, then there will be no unique direction of magnetic field. So that's why two field lines cannot intersect. Now magnetic dipole. Now as I said, magnet always exists in the form of dipole. So let's see the torque on a small needle placed in an external magnetic field. So if you keep a small magnetic needle in an external magnetic field, it will experience a torque similar to that of you have seen in case of electric field, right? So if you keep a dipole in an external electric field, it will experience a torque. Here also it will experience as a torque. Tau is equal to m cross b, and in scalar form torque can be written as mb sin theta. Same as that in case of electric field, only the symbols are different. Now here this m is obviously magnetic dipole moment. The potential energy stored in the needle is given by minus m dot b or mb cos theta. Again negative sign represents that if you are doing any external work or not. If you are doing any external work, the energy stored in the dipole will be negative. If you are not doing any work, then energy stored can be positive. Now negative sign signifies the work done by the field and not by the external force. So minus represents the work done by the external field and not by the external force. Now the net magnetic flux through any closed surface is 0 is the Gauss's law of magnetism. Now in case of electricity, E dot ds was equals to q by epsilon naught. Now in case of magnetism, magnetic monopole does not exist, so that's why it will be always be 0. So singular individual charge could exist, that's why it was q by epsilon naught. But in case of magnetism, individual charge like individual single pole does not exist, so it will always be 0. Okay, this consequence of the fact that magnetic field lines are always closed and no magnetic monopole can exist. So based on this interpretation, MCQ objective questions might come, so be prepared for that as well. Now Magnetization. What is magnetization? A circulating electron in an atom has a magnetic moment. In a bulk material, these moments add up vectorially and they can give a net magnetic moment which is not zero. The magnetization M of a sample is defined as the net magnetic moment per unit volume. So, if you consider an atom, okay, there is a positive nucleus and electron is orbiting in the around the nucleus. Now, orbiting electron can be considered to be a current, electric current, right? Electron moving. So, if electron moves, you can consider to be a current. Now, you can consider this to be a current carrying loop. So, current carrying loop means it will produce a magnetic field. Okay, now if you consider in a bulk matter, this is a singular atom. Bulk matter means you have a lot of such atoms inside a particular material, right? Now if you consider all such magnetic moment, okay, then if they are adding up, they are not cancelling each other, then the material will have a magnetism on its own. That is called magnetization. Okay, now magnetization is basically magnetic dipole moment of per unit volume. So if you take a unit volume, whatever is the magnetic dipole moment of that volume will be called as magnetization. Okay, M is a vector with dimensions L inverse ampere, L inverse A, length inverse A, okay, and it's measured in the unit of ampere per meter. Very important point to remember, ampere per meter is the unit of magnetization and its dimension is L inverse A. There is another quantity which is called magnetic field intensity, which is denoted by H. Now H is related to magnetic field B and magnetization M in this form. So B by mu naught minus M vector. Okay, the dimension of H is same as M and its unit is ampere per meter. Okay, so magnetic intensity is same as magnetization. Now it basically gives you how much, if you apply external field, how that will magnetize a particular material. That is the measure of magnetic field intensity. Okay, directly you can convert this and you can write the magnetization and magnetic intensity as M equals to chi into H. So chi is a dimensionless quantity and is appropriately called magnetic susceptibility. So magnetic susceptibility, susceptible means what? Susceptible means if someone is coming to you and saying, bro, if you study from this particular book, you will score 100 out of 100, and you just believed him, that seeing that okay, this is a very thin book, only one page book, one page note, one page questions, and you think that okay, he must be talking sense, so if I study these one page questions, I will score 100 out of 100. You studied them, you are basically susceptible to his speech, okay, and you studied it, and in the exam you could not answer a single question because not any question came from that paper, right? So this is called susceptibility. You were susceptible to his speech. But if you say that okay, suppose I gave you 10 questions and I said if you study this 10 question, you will score 100 marks. So you will say that no sir, this 10 question is not sufficient, I have to study little bit more, I have to study at least 50 questions, then only I will have a chance of scoring at least 50 marks. Right, because in the exam you have to write itself 45 questions you have to write in the exam. So minimum 50 questions required for you to score at least 50 marks, right? So if you are not susceptible, then obviously you will not listen to me, right, in such cases. Or your friend, whoever is trying to preach you, saying that okay, if you study these 10 questions, these 10 questions are only important questions, you don't need to study anything else. So that means you are not susceptible. Okay, susceptibility means how easily you can get influenced. Okay, if you are susceptible, then you can get easily influenced. If you are not susceptible, then you will not get influenced easily. Okay, so this is a measurement of how magnetic material responds to an external field. Now here this term mu r is given by mu r equals to 1 plus chi, is a dimensionless quantity called the relative magnetic permeability of the substance. It is the analog of dielectric constant in the electrostatics. So in electrostatics you have learned about dielectric constant K, right, or relative permeability. Here it is called relative permittivity, sorry, it is basically relative permeability. Now as you can see, mu r and chi are related to each other, and based on this there will be some questions in if you are preparing for your KCET exam. Now if you see that mu r equals to mu naught into mu r, okay, sorry, one mistake over here, it is mu. This is mu. Mu is the permeability of that particular medium. Mu equals to permeability of free space time the relative permeability, and if you put the value of mu r, you will get mu naught 1 plus chi. So these three quantities, mu, mu naught, and mu r and chi, mu r and chi, they are not independent, they are interrelated, okay, and only one of them is independent. Given one, the other two may be easily determined. So if any one of them is given to you, you can find the other two quantities, which is very easy. Now mu naught is a constant, mu naught is universal constant, okay. So chi, if it is given, it depends on material to material. So if it is given to you, you can calculate mu r, and if you can calculate mu r, you can also calculate mu. Now let's continue with the chapter. Now next is magnetic properties. There are three properties. Diamagnetism. Diamagnetic substances are those who have tendency to move away from stronger to the weaker part of the external magnetic field. So if you apply external magnetic field around certain substances, if it is slowly repel the applied magnetic field, very slowly, it will not repel very strongly, it will repel very slowly. So there is a tendency that it will try to come out of the magnetic field, then they are called diamagnetic substances, okay. So they have a tendency to move from stronger to weaker, okay. They will move from stronger magnetic field to weaker magnetic field, okay. In other words, unlike the way magnets attract metal like iron, it would repel a diamagnetic substance. So basically they are getting repelled by the magnetic field, so they are called diamagnetic substance. Now the very important point to remember, diamagnetism is a universal property of substances. Now all the material, all the substances that you see, they always have an inherent diamagnetism as their property. So that means you are basically, suppose I am a substance, I am an iron, okay, I have bond with diamagnetism in me, okay. So every substance have diamagnetism common, okay. Now some material, they have very strong other properties, so that the diamagnetism is suppressed. So diamagnetism is always there, okay, but some material do not show diamagnetism because they have other property which is stronger, okay. So diamagnetism is universal property. Remember this. Based on that, there was MCQ question in your board exam, so that might be there in your midterm exam as well. So be prepared. Only property which is universal is diamagnetism. All substances do have diamagnetism, okay. Now paramagnetism is the second property. Paramagnetic substances are those which get weakly magnetized when placed in an external magnetic field. So if you keep paramagnetic substance in an external electric field, they very weakly attract the magnetic field, okay. They have a tendency to move from a region of weak magnetic field to strong magnetic field, that is, they get weakly attracted by magnets. So you can consider paramagnetism is almost opposite to that of diamagnetism. Diamagnetism gets repelled, paramagnetism, they gets attracted. Now next property which is very interesting is ferromagnetism. Ferromagnetic substances are those which get strongly magnetized when placed in an external electric field, I think, yeah. so they get strongly magnetized in the presence of external magnetic field. They have strong tendency to move from a region of weak magnetic field to strong magnetic field, that is they get strongly attracted to the magnet. So ferromagnetic substances are those which we use in magnets. Okay, now let's see. The individual atoms or ions or molecules in a ferromagnetic material possesses dipole moment as a paramagnetic material. Okay, however, they interact with one another in such a way that they spontaneously align themselves in the common direction over a macroscopic volume called domain. So basically what happens is that individually all such small zones, if you consider this diagram, okay, the all small zones, they have a permanent dipole moment, permanent magnetic dipole moment. Okay, and they normally they are randomly aligned, but if you apply some external magnetic field, they quickly gets aligned in the direction of applied magnetic field and they become a magnet. That's how they behave. They shows magnetic properties. These small zones where all the molecules have a particular direction of magnetic moment is called a domain. Okay, domain means a small zone where all the molecules are oriented in a particular direction. Now the difference between paramagnet and a ferromagnet is that the temperature. Okay, basically if you heat up a ferromagnet above certain temperature, ferromagnet behaves as paramagnet. Okay, if you cool it down, paramagnet will become a ferromagnet. Okay, so this is basically the difference, whereas diamagnetism is not related to ferromagnetism and diamagnetism directly, even though as I mentioned diamagnetism is a more inherent property or more fundamental property than these two properties. Okay, what happens when the external field is removed? There is a class of ferromagnetic materials in which the magnetization disappears on removal of the external field. Soft iron is one such material. So in some cases, if you remove the external magnetic field, the magnetism that developed in it goes away quickly and they lose their magnetic properties. One example is soft iron. Okay, appropriately enough, such materials are called soft ferromagnetic material. Soft ferromagnetic material means they lose their magnetic property as soon as the external magnetic field is removed. There are number of elements which are ferromagnetic: iron, cobalt, nickel, gadolinium, etc. The relative magnetic permeability is greater than 10,000. Now there are some materials, they do not lose their magnetic property. They are called strong ferromagnetic materials. Nickel, cobalt, iron is a few of the examples. Okay, iron can be a strong magnet if you are using it in a form of steel. Okay, and if you are using as a soft iron, which is also an alloy of iron. Iron can have different alloys, right? Soft iron, then it loses its property quickly. It is a soft ferromagnetic material, and the material which retain their magnetism are called hard ferromagnetic materials. Okay, now if you see that there is a few property which actually differentiate between paramagnetism and ferromagnetism. So the susceptibility is between negative and 0, negative 1 and 0. Okay, so that is for diamagnetism. For paramagnetic substances it is greater than 0 but less than a certain positive number. It is very small. Okay, for paramagnetic substance the chi value is very small. Okay, for ferromagnet chi value is very high. Okay, for diamagnetic substances the value of relative permeability is between 0 and 1. Okay, for paramagnetism it is 1 and 1 plus epsilon, and it is greater than 1 for ferromagnetic. Now as you can see, mu is less than mu naught, which is possible. Here it is mu greater than mu naught, here it is mu very greater than mu naught. Okay, so this is a small table, comparison table. Based on that you can remember it, and MCQ questions and 2-3 marker questions, different steps, particularly in difference cases. What is the difference between diamagnetism and paramagnetism? So in that case you can use this table to differentiate between these substances. Now let's move on to the next chapter, electromagnetic induction, second chapter of the day. And as we are saying that important topics, electromagnetic induction and magnetic flux, Faraday's law and Lenz law, motional EMF, inductance and AC generator. These are the main topics from this chapter. Let us start with the electromagnetic induction. Basic definition. So electric current can be induced. Induced means what? It is induced means without applying any battery. Okay, battery, if you are connecting a circuit into with a battery, then definitely it will have a current flowing through it. Now if you can do something so that even without applying a battery, if it can produce some it can have some current passing through it, then that is called induced. Okay, induced in closed coils when subjected to changing magnetic field. So by changing magnetic field, if you can have a circuit to have current passing through it, then that is called induced current. Okay, the phenomena in which electric current is generated by varying magnetic field is called electromagnetic induction. So as you can see here, we have a coil, we have a galvanometer. As you can see, through this coil there is no battery connected in this coil, right? So battery is not involved. What you are doing, you are taking a magnet and you are pushing the magnet up and down, and as you are pushing the magnet up and down, you will see that this galvanometer will show a certain deflection. Deflection signifies that the current is being passed through this coil. So if there is no deflection, that means current is not passing, but if there is a deflection, then it represents the current is passing. So passing of current means that the current is induced in this particular circuit. Now magnetic flux, let us define magnetic flux. Magnetic flux through a plane of area A passed in an uniform magnetic field B can be written as phi equals to B dot A or BA cos theta. Okay, so if you see, this is there is a surface area through which magnetic field lines are passed, and this surface area is not perpendicular, it has some angle with this magnetic field. So for that angle, if you can calculate that angle, then the magnetic flux will be given by BA cos theta. It's a scalar quantity. Now Faraday's law of induction, an EMF is induced in a coil when magnetic flux through the coil changes with time. So if you have a magnetic flux associated with a coil, if you can change that flux, then there is an induced EMF. The magnitude of the induced EMF in a circuit is equal to the time rate of magnetic flux through the circuit. So epsilon is basically the induced EMF. We denote epsilon by as EMF, right? So EMF is equal to minus n d phi by dt. Now according to Faraday's law, this minus sign does not come, the negative sign comes from the Lenz law. Okay, but anyway, this is the correct mathematical form. Faraday's law just states that this is basically n d phi by dt. Now what is this n? By the way, n is the number of turns. So if you have only one coil with only one number of turn, then n equals to 1. But if you have say 10 coils, okay, each are wrapped around, then n will be equals to 10. N represents the number of turns, phi represents magnetic flux, and d phi by dt represents the change in magnetic flux. Now Lenz law is very important. The polarity of induced EMF is such that it tends to produce a current which opposes the change in the magnetic flux that produces it. This is the consequence of conservation of energy. The negative sign is basically coming from this Lenz law. So what does it mean? It means that if you have, suppose you have a north pole, you have a coil, you are pushing this north pole towards this coil. Okay, so there will be an induced current in this coil according to Faraday's law, right? Because the field lines which is coming out of this north pole passing through this coil, that number varies. So that number varies means the magnetic flux linked with this coil also varies. Okay, if the number magnetic flux linked with this coil varies, it will have an induced current always. Okay, if the magnet is static, then what will happen? If the magnet is static, then no magnetic flux linked with the coil changes, so change of magnetic flux is 0. In that case, the induced EMF will also be 0. So if the magnet is static, nothing happens. If the magnet moves towards or away from based on the direction, okay, there will be a direction of induced current as well. Now Lenz law says that if you are pushing a north pole towards this coil, then the current direction of current in this coil will be such a way that there will be a north pole developed in the near end of this magnet, so that these two poles will repel each other. Okay, so this north pole and this north pole, they will repel each other, so that you are trying to push it towards it, but you have to face some difficulty because there is a north pole which is developed over here. Okay, this north pole and this north pole will be repel each other. Now what will happen if you take the same magnet, same north pole, now you are pulling it away from this same loop. Loop is same, magnet is same, even north pole facing the loop is same, but instead of bringing it towards the coil, now you are pulling it away from the coil. So in that case, there will be a south pole generated, so that again you face difficulty that this north pole and this south pole, they will attract each other, and again it will try to stop this motion. So basically nature is trying to stop this motion and trying to stop induction. Okay, this is basically conservation of energy. Why so? Because the current which is being produced, that consumes some energy, right? It requires some energy to produce this electricity. Now imagine that you push this magnet, somehow a south pole developed over here, they get attracted, and the magnet automatically gets attracted towards it, and then as soon as it goes away, it will try to repel it, attract it again. So there will be automatic motion, and you will get a electric current out of nothing. Okay, you just initially pushed it, and then you are getting current again and again, which is not possible, right? So you are getting electricity without doing any work, which is physically not possible, conservation of energy wise not possible. That's why, to prevent that energy conservation of energy, the Lenz law is always acting. Okay, this is a law, it is not something he analyzed it. Okay, it is, even if he has not analyzed it, this law is still there. Okay, so like Newton's laws of gravitation, it is still there, right? Even if had Newton not discovered it, it will be still there. So he just discovered it. It is not like something which is was not there before Lenz discovered it. It was already there. Okay, so this is the few things that you have to understand. Now motional EMF induced in a coil. So suppose we have a rectangular sheet, rectangular railway, okay, and you are trying to bring this is your train that you are trying to push it along this railway. The railway lines are closed, there are some magnetic field here. Now if you try to bring this rail along this path, then there will be some induced EMF across the ends of this wire. Okay, now this is called motional EMF. So if you move this, there will be some induced EMF, and you can use that EMF based on your requirement. Now the expression for motional EMF is minus BLV. Now this is a very common formula for numerical questions in your KCET or JEE exam, but the derivation is very, very important for your board exam. We will be doing this derivation in my next lecture, not in this lecture. This is just a theory division, so we will do the derivation in our next lecture as well. Now let's continue. An electric current can be induced in a coil by flux change produced by another coil in its vicinity, or flux change produced by the same coil. Okay, the flux through a coil is proportional to the current, that is phi b is proportional to I, or d phi b equals to proportional to di by dt. So what happens is that you have one coil. Okay, if you bring a magnet, you are producing some induced current. Now instead of using another magnet, what will happen if you use a second coil? Okay, now coil, in this case the coil has a battery connected to it. Now that means this is a coil which already have a electric current associated with this coil. So if there is an electric current passing through a coil, there will be a magnetic field inside this coil, right? We have learned that in moving charges and magnetism chapter. So if there is a current passing through this coil, there will be a magnetic field developed over here. Now if you push and pull this coil, okay, then there will be a change in magnetic field through the second coil, and because of that this coil will now have a induced EMFs, and this induced EMF is basically proportional to how you are changing the current in this particular coil. Okay, so this relationship is called inductance. Okay, it is also possible that EMF is induced in a single isolated coil due to a change of flux through the coil by means of varying the current through the same coil. Now we do not have two coils, we only have one coil. Okay, so first we started with magnet. Okay, now we removed the magnet, we added one another coil instead of the magnet, and we did the same experiment. Now we even removed another coil as well. We now have only one single coil through which current is already being allowed to pass. We have a battery, basically we have some battery attached to it, and the current is being allowed to pass. Now even in this particular case, this current will induce a magnetic field, and it will try to send a induced current in the opposite direction. Okay, an induced current in the opposite direction. Okay, so this is called self-inductance. Self-inductance. So self-inductance is also possible, and the formula for self-inductance is epsilon is equal to minus L di by dt. Now as you can see, the self-inductance only occurs when this current changes with time. If this current remains constant, then self-inductance does not occur. Okay, self-inductance is very important in many of the applications in our day-to-day life. EMF, this EMF is also called back EMF. Back EMF means if the EMF is trying to send the current in this particular direction, the back EMF is trying to send the current in the opposite direction. That's why it is called a back EMF. Now work needs to be done against the back EMF in establishing the current. For the current I at an instant in the circuit, the rate of work is half Li square, and this work will be stored as a form of potential energy. So the potential energy of a coil is basically given by half Li square. So this is a very common formula. You have to remember this formula. Based on this, in a small 2-3 more numerical questions or even MCQ questions might come from this concept, right? Now let's move on to the last concept, AC generator. An AC generator converts mechanical energy into electrical energy. The induced EMF for a rotating coil of n number of turns is basically given by epsilon is equal to NBAW sin omega t. This is a simple formula, and here you can write it as epsilon naught is equal to NBA omega. Omega is the how fast the generator is rotating, right? So in the last chapter we have read that if you have a current carrying coil, you keep it inside a magnetic field, it will experience a torque, right? So here you are using the opposite case. We are rotating the coil, which is already basically you are applying a torque into it, okay, and because the magnetic field is already present, if you rotate it, okay, because of the motion of the coil, it will have an induced current into it, okay, and that induced current is basically that we are using in our life everywhere. Okay, so there is a source which is trying to rotate the coil. Now many cases the rotation happens due to various factors. One of the very common thing is that the water that flows, okay, into from a dam. Now that water from a dam actually rotating the turbines. Now turbines rotating in a very strong magnetic field, and basically it induces an electric current, and that current is being transferred to our household. Okay, this is one of the very common source of electricity. So AC generator is the something which is basically responsible for our everything in our life, okay, including you are watching this video because you are able to charge your device through this current generated through the AC generator. So AC generator is basically the fruit of electromagnetic induction. So electromagnetic induction is one of the most important used concept in our practical life as well. So I hope you enjoyed this session. I will be back with all the questions from these two chapters. If you have any doubts, any questions, please mention in the comment below, and also if you have not yet subscribed, don't forget to subscribe to our channel. I will be back. Till then, bye.